can go with audio, enlarge the video, up and running. So problem one's going to be a volume of revolution problem. And as we continue to work with them, I'm hoping that the calculation comes into view more easily for you, that we begin to see the patterns and understand conceptually what's going on. It takes time. It seems to be breaking down into a pi from A to B, big R squared minus little r squared dx, or volume pi C to D, big R squared minus little r squared dy. So how do you determine whether you're going to be doing dy or dx? Well, you look at the radius. One radius of revolution. So if I'm rotating above this axis up here, right, I'm rotating around the wall. Let me blow up that radius, and it's really a rectangle. I'll make it bigger. I'll fill it in. And the question is, what is this width? Well, it's moving horizontally. If it's moving horizontally, then it's got to be done in terms of x, which means that this y value then has to be written as a calculation based on x. And that becomes either our little r or our big R. Over here, again, radius. If we're going to stack them vertically, lots of radiuses, stack them vertically, then I'll enlarge the radius, I'll color it in. That is what I'm depicting right there. What do I have? I have a width, but what is that width? It's vertical width, so it has to be a dy problem, which means that we're looking at these x distances, tacking them on to the empty space distance, right? We're looking at these x distances, and those x distances actually have to be a function based on the y values, a calculation based on the y. That's what we're trying to get at. So I'll give you a problem. I'll give you some parameters, and then you can pause the video and try it at your own pace, and then go through it with me. On Monday, you'll go through it with your classmates and explain it to each other. But right now, we're looking at y equals 0, y equals 6 minus x, y equals the square root of x, and we're going to rotate it around x equals 10. All right, you pause the video. I'm going to draw the picture now. So there's x equals 10. That's my axis of revolution here. That's my axis. I've got 6 minus x, so let me get an x-axis going here. There's the x-axis. Oh, I'm sorry. I meant to call it y equals 0. There's y equals 0. There's 6 minus x. Right there. There's 6 minus x. And then there's the square root of x. And I think we're after this area. So this is 6 minus x equals y. This is that one. Oh, but I want the x distances. Oh, so I guess that's 6 minus y equals x. So this is 6 minus y. And I've also got the square root of x equals y. Oh, but I want this x distance here. I want that x distance because then I know how far I am actually from here to here. So what defines that x distance? Well, that x distance is defined by y squared. Oh, so if y was 1, then that distance is 1. Okay, so I don't want to call it a function in terms of x. I want x as a function in terms of y. Ah, geez. So I think that my big R is one of these. That's my big R. Ah, so I got to be able to nail that. I got to nail that. And I guess I'm not doing this in terms of dx's, right? I'm doing it in terms of dy's. So since I already have this written up here, I might as well take it. So now I'm going to push this to the side a little bit. I'm going to do pi a little bit further out. And now I'm going to do big R squared, little r squared. Right? I'm going to replace big R squared with a statement minus little r squared with a statement. Might as well figure out from what to what. Oh, okay, I didn't connect that too well. Oh, but I'm not doing this in terms of horizontal. Oh, I'm doing this in terms of vertical. I guess I need to know what that y value is. I guess I need to know when 6 minus this y value, that y value. Well, I can see it's 2, right? Without having to put them equal to each other and factor. 6 minus 2, right, is an x value of 4. And 2 squared is an x value of 4. So, okay. So I now know that this is the coordinate 4, 2. But because I'm doing it in terms of y, I don't care about that. All right, so now the question is, what is big R? How do we do it? Geez, I know when it was X, it was top minus bottom. I remember we said yesterday, right minus left. Oh, right. That X distance is 10, right? Left. Oh, where was I? Oh, 0. So this X distance is 0. Oh, that means that this radius is actually 10, and this one is actually 8. That's 8 units. This is 10 units. No, squared. I forgot to square it, 4, right? Oh, yeah. So up here, that would be an X distance of 4. If I take 4 away from 10, that's my little r. Yeah, connected to this. Okay, talking too much. This is what you should have had. Big R, 10 right minus left. 10 minus y squared, there's your big R, minus little r. Little r is the inside edge. 10 minus 6 minus y. Again, this is one you got to put in parentheses. Squared. Easy to forget the squares, easy to forget the pi, easy to forget the 0 to 2. Lots of places where it's easy to forget something. So I just forgot what I said. Oh, next problem. I wonder how many of you got that right with so many easy things to forget. Whew. God, this study, you have to actually have some mindfulness. Wow. As you get older, well, that's another story. Next problem, let's see. Of the newer material that we're doing. Good clean board here. Good enough. I like the old erasers better. So let's say we got a function, f of x, and that's equal to x cubed minus x squared plus x. I got plus 10. And g is the inverse, and we're going to find g prime of 16. G prime of 16. Pause the video, you'll go get it. All right, so hopefully it doesn't take you too long to figure out that f of 2 actually equals 16. And f prime of x, I might as well put up here, f prime of x is equal to 3x squared minus 2x plus 1. Okay, if I put a 2 in there, f prime of 2 is equal to, guess I got to do it. 12 minus 4 is 8 plus 1 is 9. Make sure I got that right. 12 minus 4 is 8 plus 1 is 9. Yeah. All right. So if I made any mistakes, you can email me. So therefore, I know that g of 16 is now 2. And I know that g prime of 16 is now not 9 to 1, but 1 to 9. That's what I know. Okay. Next problem. Okay, erase the board. Boom. Boom. Put some muscle in it there. That's actually better. All right. Next problem. What have I got? I got, the ladder being pulled away from the wall. So there's the floor. There's the wall. There's the wall. I guess I'll fill in the floor so nobody trips. There's the ladder. I'll even put another leaning against the wall, and it's being pulled away from the wall at 3 feet per second. That means this distance is increasing. Okay, and the ladder is 13 feet. Ladder is 13 feet long, and at the instant that the ladder is about 12 feet from the wall. When 12 feet from the wall, at what rate is the ladder coming down the wall? All right, you pause the video, give it a go. Let me erase this. All right, so you're trying to look at it. Well, first thing you want to do is set up a little geometric relationship. Let's call that y, x, y, and let's call that z. Let's put this thing in motion. That means x squared plus y squared equals z squared is the geometry of the situation. Putting it in motion gets us 2x dx dt plus 2y dy dt equals 2z dz dt. Again, there's a nice video out there about implicit differentiation and how the numbers work in y. If you want to get inside this a little bit more so that you can actually see and get a feel for the numbers, go back to that video and have a go. I'm going to divide everything by 2, make life easier for myself. Then I'm going to solve this for a 13-foot ladder, and when I'm 12 foot from the wall, if you take your time with that, you'll see that a 12, 13, 5 is one of our famous Pythagorean relationships. You would have taken more time with it, but that's what you're going to find out. So when x is 12, that means I can come in here and I can write 12 for x. I now have solved for y. So dx dt, we were given dx dt when it said that that is, I erased it. Oh no, here it is. This 3 feet per second means that that's dx dt. All right, so therefore I can now come in here with 3 feet per second. I'm not going to put the units here because I'm running out of space, but they work out as well. We now know that y is 5. We got to find dy dt. This is what we're trying to find, dy dt. And the change in, and z is 13. What is dz dt? It's a 13-foot ladder. That ladder is not changing at all. All right, there's no change. it's a 13-foot ladder. It's constant. All right, so we could have come here with this immediately. Probably should have. I probably should have written that instead of z. Okay, so nothing, no change over there. So we're down to one variable here. And so if we, well, can you see it? Yeah, you're still within sight. So 36 goes to the other side, becomes minus 36, dividing by 5, and dy dt. The negative signifies that it's coming down at 36 feet every 5 seconds. So dividing that in it by 5, it's a little more than 7 feet per second. All right, and yeah, the further this comes out, the more time gravity's had to work. It's picking up some speed. Okay, that's why you don't want to fall from any great height. You really pick up speed. Okay, so you would not say it's decreasing at negative 36 every 5 seconds. You would say something like it's decreasing at 36 per 5, okay, feet per second. Or you just say, you know, leave it alone. Say it's moving at a rate of minus 36. You don't want to do a double negative there. All right, we'll hopefully say that more clearly as we go along. So that was a related rates problem. I did one for you like that 2 or 3 days ago, so I got away from it, came back to it, and hopefully some of those memory banks were working, but it takes a while to learn how to do that. Next problem. We'll do again, come back to something we did before, and let's see if it's in your memory banks. But I'll change the number slightly, and you go after it and try to prove that here's the Rio Grande again, you know, and we got fence, fence, fence. How much fence do we have? We want to make a rectangular pasture area for our steers. And let's say we have 400 feet of fence. 400 feet of fence. So how do you configure it so that you maximize the area? So we got a max-min problem. Gee, I wonder how we solve max-min problems. Integration or differentiation? Differentiation. So that's an x, that's an x. That's going to be 400 minus 2x. Hopefully that reminds you of some of your Algebra 2 and Algebra 1 word problems. So we're looking at a calculation here where area is equal to 2, let's see, so x times 400 minus 2x is going to be minus 2x squared, right? That times that, plus 400x. Now from our algebra, we know we got a downward shaped parabola. We're looking for a slope of 0. So a quick way to prove this is concave down with a slope of 0. So we're going to look at 2 derivatives here. Get my eraser going. All right, so we're going to look at Derivative 1, a prime. A prime is equal to minus 4x plus 400. And a double prime is equal to minus 4. What's the significance of a double prime negative 4? Well, if the second derivative is always negative, we've got a concave down shape. When do we have a slope of 0? We have a slope of 0 when x is 100. So when x is 100, that's what we're looking for. We've just proved that that's going to create a maximum. So if you had 100 here, 100 here, and subtracting 200, that's how you're going to maximize the area of that pasture. What's the next problem? Next problem is equation of a line tangent. Let's put some muscle into it. I got to get those other erasers. Here we go. Saves me moving the camera. I don't know which is better, having every problem on the board and moving or doing the erasing. Repetitions, my friend, I'll figure it out. ELT, equation of a line tangent to y equals, how about we do the arc sine function? The arc sine of x. I don't really need to write the e. Arc sine of x at x equals negative root 3 over 2. Try to cram in some review from previous work, which some people did and some people didn't do. Should have covered this. But it seems like a lot of people don't have a working knowledge of that. We'll try to develop it over the next few weeks. So that's what we got. Doesn't hurt to know what the arc sine looks like. The arc sine function is the inverse of the sine function from negative 90 degrees to 90 degrees. And this is a one-to-one relationship there. And inverses actually are symmetric to y equals x. So y equals x would split the inverses. So what I just drew was a graph of arc sine, and it looks something like this. That's what the arc sine looks like. We have angles on the y-axis. We have ratios on the x-axis. So we went -1 gets us minus 90 degrees or minus pi over 2. Quick review here. +1 gets us +1. The arc sine of 1 is 90 degrees or positive pi over 2. I'm trying to get some of these thoughts in the noggin. All right, so where's negative root 3 over 2? Negative root 3 over 2 is negative 0.87, so we're in this vicinity. We want the equation of that tangent line to this curve. We can see that our slope is positive. When we do our work, if our slope isn't positive, we probably have made a mistake. And it sure looks like if this is 90 degrees, negative 90, then maybe minus 60 without doing the calculus and the algebra and everything else, just looking at the graph. So let's do the work. Arc sine of x. We need y prime for slope at that instant. So y prime of x is 1 over the square root of 1 minus x squared. So let's find the slope right now. 1 over the square root of 1 minus negative root 3 over 2 squared. All right, so that's 3/4. After I square it, that's 1/4. Square root of 1/4 we did in class the other day, that's 1/2. I now know my slope is 2. For that tangent, I know the x value, minus root 3 over 2, so I write positive root 3 over 2. That's the first step in conversion is subtraction. If I subtract that out, I want to bring in the value of the arc sine of negative root 3 over 2. Again, another crash course. The arc sine is the right side. I have 0 degrees here. I move in the negative direction to negative 90 in that direction. That direction is positive 90. This is negative root 3 over 2. That's my input. And what is that angle? What is that angle? That angle is indeed minus 60 degrees. Minus pi over 3. That matches up with the tangent, which gives us information about the rate of change at that instant. Okay? All right, that's what it is. I'm gonna put some muscle in it again. Just getting that, just getting that, getting that, getting that. This isn't my classroom, so I'm gonna have to clean this board well. I don't want Mr. Ward not to have a nice clean classroom when he comes in. He's been here since, I think, the turn of the century. And this is his last year. He's retiring. So we gotta send him out with a nice clean board. All right, so next question. Can you integrate 2x over 1 plus 9x squared dx? No, that's not what I want. That's not what I want. 1 plus 9x to the 4th. That's what I wanted. And that's what I think I wrote, but I can't see it from here. All right, so pause the video, give it a go. All right, so the kicker here is u equals 3x squared. If you have that, then you've got 2x over 1 plus u squared, and my du is going to be 6x equals dx. So therefore, I now have 6x du over 6x. Oh, I can see that that becomes 1/3. Sure looks like an arctan of u to me. From u to me. Oh, arctan, which you haven't done a whole lot of. What was u? 3x squared. How do you check it? Take a derivative. Let's take a derivative. It's easier to take the derivative than the integral. It's easier to spot because it's just mechanical. So 3x squared becomes 6x in the numerator. 1 plus the square of that is 9x to the 4th. We're multiplying that by 1/3. 1/3 is, yeah, came right back to what we started with. 1/3 of 6x is 2x. Yep, looks like we checked that from a different perspective. It's definitely right. All right, so that's the problem you're going to do. All right, 2 more problems. So with that in mind, y equals tan inverse of 8x squared. Would you please find y prime? Okay, pause the video, go after it. I'm hoping you recognize that tan inverse is the same thing as saying arctan. Okay, so it's the same thing as saying find the derivative of the arctan of 8x squared. All right, so we take the derivative of the argument, which is 16x, 1 plus, we square it, 64x to the 4th. Done. Next problem. Okay, last one. And hopefully you got a little practice tonight on your own, slowing the pace a little bit. So can you integrate? Let me make sure I got this right. 9x over the square root of 1 minus 64x to the 4th dx. Pause the video. Same as arctan, really. It's the same process. You just have to recognize that u is 8x squared, so du is 16x, and that's a new name for dx. And maybe you can see 9/16 coming out, the arc sine of 8x squared plus c. That's what you're after, but let's take our time with it. So dx becomes du over 16x. 9/16 comes out. Gone. U, 64x to the 4th is u squared. That thing squared. This is now gone. Yes, so that became a 1. And now we can see the arc sine of u, right, plus c times 9/16. 9/16. Then you replace u with 8x squared. Okay, we take the derivative to check it, make sure we didn't make any careless errors. 9/16 times 16x over the square root of 1 minus, square that, 64x to the fourth. What happens to the 16s? The 16s cancel. I now bring 9 in. And now the question is that where we started? Oh, I erased where we started. Assume it is. That was it. That's your new practice. So let me shut that down.